Today, I'm very happy to share our work with you. Many verb-oriented common sense knowledge. Common sense knowledge plays an important role in artificial intelligence. However, common sense is difficult to obtain because it is a human consensus and rarely explicitly appear in text and or the other data. Most of existing methods are limited to acquire knowledge directly from corpora so that they can only extract explicit common sense knowledge, without the ability to harvest the implicit knowledge. And besides, the number of variations in the existing common sense knowledge base is often limited, since most of them are predefined by hand. For example, there are only about 6 variations in WordNet and 13 6 variations in ConceptNet 5.5. Thus, in this paper, we focus on the automated acquisition of a typical type of implicit common sense knowledge that is verb-oriented, like person eat food. Specifically, a knowledge-driven approach is proposed to mine verb-oriented common sense knowledge from verb phrase, which consists of subject, verb, and object. The core idea of our approach is to conceptualize subject and object separately with concept in a large-scale taxonomy known as per-base. For example, person eat food can be acquired by conceptualizing the verb phrase John eat bread with John is a person and bread is a food. However, there are still several challenges for the acquisition of verb-oriented common sense knowledge. First, how to determine which verb phrase can be generalized to the verb-oriented common sense knowledge. In fact, not all input verb phrase need to be conceptualized as common sense knowledge, since some verb phrases are already abstract enough. Second, how to select an appropriate concept for instance. In general, a system always has thousands of concepts. Some concepts are overly specific and others are overly abstract. Third, how to measure the plausibilities of the generated verb-oriented common sense knowledge in terms of semantics, after conceptualizing subject and object respectively. Next, we start to introduce our method. In Figure 1, our system accepts verb triples such as Harry eat apple, John eat bread, Michael eat egg, and man eat fruit as input, and outputs verb-oriented common sense knowledge such as person eat food. To solve the above challenges, we designed 2 modules. The first is an attribute-based triple filter used to solve the first challenge. For example, in Figure 1, the verb triple man eat food is filtered out since man or food are overly abstract in per-base. The second is a verb-oriented common sense knowledge generator used to solve the second and third challenges. For example, in Figure 1, person eat food can be mined from the filter verb triples. In the attribute-based triple filter, we aim to filter the noise verb triples if the subject of the objects of an input verb triples is overly abstract. The basic idea of measuring the abstract degree of a term is to use an absolute level in a taxonomy. However, There are lots of isolated subtaxonomies in taxonomy, which makes it unreasonable to design compare the absolute level of true terms in different subtaxonomies. Thus, we need a more flexible method to measure the abstract degrees of a term. In taxonomy, there is a phenomenon where the level distribution of hypotheses of a term at lower levels tends to be uniform, while at higher levels is usually concentrated. Formally, we employed an attribute-based metric to formalize these regularities. In Verb-Oriented Commonsense knowledge generator, we carefully designed a joint of optimization models with objectives developed upon the MDLs and the neural language model. We employed MDL to select appropriate concepts that are neither specific nor abstract for a given set of subjects or objects. For example, in Figure 1, given a set of subjects, Helen, John, Michael, person, and name will be generated with MDL, while abstract concepts like character or specific concepts like student will be discarded. Formally, let function L be the description length to encode subjects T with the concepts C. A two-stage encoding schema is used to minimize function L. The first item in the equations is to encode the concept C, and the second item is to encode the subject T with the help with C. We use neural language model to evaluate the plausibility of the generative verb-oriented common sense knowledge. For example, in Figure 1, the unplausible candidate triples like lamb eat food and the person eat complete will be filtered with neural language model. Specifically, we employed LSTM to build a language model and use Perplexity to evaluate the performance of LSTM. To reflect MDL and neural language model, we designed a joint optimization model. In the equations, the first and second action are to conceptualize a set of subjects and objects, respectively. The third item is to evaluate the plausibility of the generative-oriented, verb-oriented common sense knowledge. Where lambda is a parameter used to adjust the variance between MDL and the neural language model. Next, we start to analyze the experiment. We use 3 real-world datasets to realize our solution. First, probabilistic taxonomy. We choose probabilities to provide concepts for the subject and objects of input verb triples. Second, verb face data. We use the English all part in Google syntactic anagrams to extract verb phrases. Third, training corpus. We use Wikipedia to pre-train the neural language model. To evaluate the effectiveness of our approach, we can compare it with 3 baselines. The first is the MDL method. The second is the neural language model. And the third is combined by the conceptualization mechanism proposed in other words and our neural language model as a new method called CMNLM. We report the mean average qualities as a metric for a set of verb-oriented common sense knowledge, which is the mean of the average score of volunteers for each verb. Now, we report an overview of our mind verb-oriented common sense knowledge. We fill the node frequency the verb to ensure the accuracy of the inputs. In practice, we fill the noise verb with the frequency let bracket v right bracket less than or equal to 3, where frequency is left bracket v right bracket is the frequency of the verb v in all verb phases. Finally, with just 2,423 verbs and 126,367 verb phases. With our solutions, we harvest 2,059 verbs and 18,406 verb-oriented common sense knowledge. In Table 1, we list several typical verbs and their common sense knowledge. We select the top 100 verbs of the highest frequency to compare our models with baseline, including MDL, NLM, and CMNLM. The result is shown in Table 2. We can see that our model has achieved a better performance than competitors. Furthermore, we compare our mind-oriented common sense knowledge with other typical common sense knowledge base in terms of variations. The results are shown in Table 3. Compared to other common sense knowledge base, our mind common sense knowledge have two characteristics. First, the number of our variation is up to 259, far exceeding that of other knowledge base. Second, most of the variation found by our solution are not in the competitors. That is, most of the verb-oriented common sense knowledge is new knowledge, never found. Finally, we conclude our work. In this paper, we focus on typical kind of implicit verb-oriented common sense knowledge, which rarely appear in corpus. To this end, we propose a knowledge-driven approach to mind common sense knowledge automatically from verb phrases with the help of the taxonomy. First, we designed an attribute-based filter to cope with noise input verb phases. Then, we propose a joint model based on MDL and NLM to generate verb-oriented common sense knowledge. We conduct extensive experiments to show our solution is more effective to mine the verb-oriented common sense knowledge than competitors. And finally, we harvest 18,000 verb-oriented common sense knowledge. Thank you very much.